Listo.
Gracias.
¿Quieres que ya empiece a aceptar a la gente que va llegando?
Si querían y me dijeron,
In my watch, it's so very
I think,
Okay, I think that we should start this special seminar, LANIMFE seminar. Oh, should if I see. So I will be the chairman for this seminar, and it's a great pleasure for me to introduce Professor Gerhard Naegele from Forschungszentrum Jülich. And let me read what a brief vita. Gerhard studied physics and mathematics at the University of Constance, closing his studies with a master's diploma degree in physics and a high school teacher's degree in mathematics and physics. Subsequently, he started his PhD student work on colloidal mixtures at the physics department in Constance, under the supervision of Professor Prof. Klein. During this period, collaboration started with Magdalena Medina Noyola, José Luis Arauz Lara, and Honorina Ruiz Estrada, supported by various visits of Gerhard, to the Simvestab in Mexico City. After receiving the PhD in physics, he spent a postdoctoral year at the University of Michigan in Ann Arbor in 1989, working with Professor Silla Akchasu on the dynamics of polymer melts in the period 1990 to 2000. In that period, 1990 to 2000, he was employed at the physics department of the University of Constance, first as a research fellow and subsequently as university lecturer. During this period, he got to know José Miguel Méndez Alcaraz and later Ramón Castañeda Priego, professors both, who worked in the group of Klein as PhD student and postdoc, respectively. Since 2001, he is staff scientist at the Forschungszentrum Jülich in a submatter group headed by Jan Dont until 2022, jointly with holding a professor of theoretical physics position at the University of Düsseldorf. His current research work is on the structure and dynamics of ionic microgel systems, SAL air short range, attraction long range, repulsion protein dispersions in 3 and 2 dimensions, cross-flow filtration modeling, and post-synaptic neuronal signal transduction. This is what I have written here. I also want to add yeah, that's true. We have 40 years of having met the first time Gerhard and the Mexican community of soft matter, an important component of it, and that was mentioned here. And so it's a really great pleasure to have Gerhard with us. Yesterday we had Jan Dont giving the colloquium, and now Gerhard. I think that I cannot add much to except to say that besides the very fruitful scientific collaboration with the Mexican community, Gerhard has been a great friend of us, and he looks more Mexican than many. Although I must say that it was not natural. The very first time that we met, I think that José Luis and José Luis Arauz Lara used to do theory. And when he was doing theory, he was a very practical guy. And if to understand something, he had to to approximate things, even if the approximation meant violating any law of physics. But we are doing theory. I mean, just imagine that the h bar equals 0 or something like that. And Gerhard was how to say, a well-educated, mathematically highly educated physicist and very rigorous. and this poor Gerhard couldn't believe that in the blackboard we could violate anything. And this guy and that was a really nice way of having, we learned a little bit of rigor, not much. And he learned a little bit of tropical approach to science. And so it was a beautiful interaction between not only Gerhard, but also people from Germany. But more, I'm just mentioning and saying the great pleasure that it was, at least for me, but I'm sure for many Mexicans that work in soft condensed matter. Okay, the introduction is over, and now I give, yes.
We didn't violate anything. We just
pretended.
Approximation.
Yeah, because we are being recorded. That's right. Thank you. Okay, Gerhard, you're very welcome. We are very happy to have you.
Thank you very much, Magdalena. I will follow you for a very kind introduction. I think it's an word.
I think that you should. Okay.
Okay. Thank you very much for the very kind introduction. It's really I'm very pleased for the kind invitation together with Jan to visit some of the Coloquio, plus different places we are going to see in the upcoming days. So thank you very much for that. And I hope this is also an example of a profitable presentation. So my presentation is about theory and simulation of dispersions with competing interactions. We will create both three-dimensional dispersions and quasi-two-dimensional dispersions. And I'm going to say what I mean by quasi-two-dimensional dispersions. So, okay. This is the content of my talk. First, I will deal with three-dimensional dispersions, so-called FAR systems. That are particles which have short range attraction, SA, and at the same time a long range repulsion. And these two types of interactions are competing, meaning that they have the same interaction strengths. We will particularly focus on a computer simulated study of such systems, and we will study the structure and dynamics. The simulation method which we are going to use is the so-called multi-particle collision dynamics method called MPC, which is a method where a solvent into which the particles are dispersed is actively treated. And we will then at the end not only do simulations, but we will also compare with experimental data done in a group of Naegele in Delaware, USA, about licensed by homogeneous solutions, which, when they are considered under low salinity conditions, are a nice example of FAR systems. And then I will proceed to quasi-two-dimensional systems. I will say later exactly what that means. That means basically just that we consider FAR particles which are confined to motion within a plane, but there's solvent on top and below of that plane. And since there's solvent, three-dimensional solvent, which is this monolayer of SIL particles are embedded, we're talking about the broadside two-dimensional dispersion. Again, I will to study the phase behavior and the glass moving structure of the systems, and then we will compare results with and without the interactions. What that is, I'm going to explain before. Okay, let's start with three-dimensional dispersions. Okay, here we go. Yeah, these are particles which are circular and they're in the spherical, which are spherical and they interact by a combination of the short range and potential with 1/2 to 100, extremely steep repulsion and a very short range interaction, so like 1 over the distance to the power. So the generalized non-natural potential used. And then we have a long range repulsive interaction potential, which is basically a screened Yukawa potential characterized by screening parameters psi and an amplitude factor A, which is proportional to the charge on that particles. What I have in mind completely are proteins, and this is a lysozyme protein. It has hydrophobic and hydrophilic patches on it, and it is charged. In this case, positively charged. And if you don't care too much about the spectrum, you can describe it approximately by a homogeneously charged field. And then the potential which we have used here is actually not a bad description under the condition that we are in a low salinity regime. So most of the ions in the suspension have been taken away using ion exchange residue. The range of the repulsion units of the diameter sigma is 1.8. So this is roughly this here, and the range of refraction is this here is much smaller. So we have really a system with short range repulsion here, seen by the minimum, and a very long range, short range refraction and a very long range repulsion. The parameters characterizing this potential is an effective temperature, T star, which is 1 over epsilon, and epsilon is the strength of this refraction in units of kBt. This is roughly given by kBt, the form energy, divided by the minimum of the potential, which grows with increasing epsilon according to this law. Okay? And as I said, this potential, I will refer to the generalized linear change in Barber potential, is actually a quite nice description of low salinity aqueous solution of proteins like this, like that. All right. Okay, this is the phase diagram, which has been mapped out for a certain range of temperatures and volume fractions. When you are at high temperatures and low volume fractions, one fractions are the area taken by the particles relative to the area of the solvent. Then you are in so-called dispersed fluid phase, where the particles remain there in reality, there's no rapid formation. Now, if you then are in this dispersed fluid phase and you increase the concentration, then you end up in a percolated phase where these particles form space between vessels called random percolated phase. If you then are in this random percolated phase and you lower the temperature again, or let's say you are in the dispersed phase and you lower the temperature, then these particles tend to form clusters of a preferred size, and then you are in a different phase called the equilibrium cluster phase. And if you then increase the concentration again, then you go from the equilibrium cluster phase to a percolated phase again, but this space between clusters are then formed not by individual particles, but by clusters of particles. So this one cluster percolated to space between clusters, called the cluster percolated phase. There's a line separating the non-cluster phase, so these two from the two non-cluster phases. I'm going to talk about that a little bit later. How can we identify these phases and that we done earlier by others? You determine the cluster size distribution function, which gives you the fraction of particles forming as clusters, as a function of the number of particles in the cluster. So when you are in the dispersed fluid phase, you have this blue curve here. There's no, the maximum of NFS is at a single particle, so it's monomer dominated and it decays quickly. When you are in the equilibrium cluster phase, then you find clusters of preferential size. So you have here a secondary maximum here at a cluster size of 11, meaning that the majority of clusters have a size consisting of about 11 particles. Okay, when you are in the random percolated cluster phase, it looks similar to the dispersed cluster phase. We have no maximum. However, you have here a peak, in our case at 1000, which characterizes this basically cluster. In our simulation here. only one carbon particles have been equal. Here in this last coordinated phase, you have defined a cluster size distribution function, which looks really roughly like that. So these are the relations to the done by Ramon Castaneda from Lyon, and together with the group of Naegele. What they found is that you find maxima at different cluster sizes, and again, on top of that, you find the maximum at the space between clusters. You have this characterization that this space between clusters is consisting of smaller clusters of different sizes. Okay, good. Now, this line here, which separates the unclustered two phases from the two clustered ones, has been obtained by the following simple idea, which I think is quite nice idea. The question is, why are these clusters here in this phase of finite size? Well, there's a competition between attraction, which would like to trigger a microscopic phase separation into a gas-like phase, conformation phase, and a liquid phase. However, this microscopic phase separation is frustrated by the presence of the long-range diffraction, which limits the growth of the clusters. So, one must trying to find a lining where you only consider the attractive part of the fair potential, basically. And so for this, then you can calculate the binodal line, gas liquid coexistence line, and if you do that, you find this line, which is roughly speaking, indeed separating the two non-clustered phases from the clustered phase. Right? Okay, good. So far, so good. Okay, now with this computer simulation that I mentioned, this multi-particle collision dynamics simulation, which is a method where you simulate the particle dynamics simulation box with the solid explicitly considered. This is important for the dynamics, not so much for the status, but we also use this method to calculate static properties, which is not the fastest problem, I must say, but which are the hand. So now this is now part of the phase diagram where we plot the coexistence between the cluster fluid phase and the dispersed fluid phase. So here we have cluster theory, and this epsilon characterizes the strength of attraction, and here we have basically the volume function. You see here when you run higher attractions, then you run the clusters. And here again we plot the cluster type distribution function. And you see for epsilon from 2 kBt up to 7 kBt, units of kBt, the system is 4 kBt here. The system is 2 and 4. The system is basically the dispersed fluid phase, where you have only monomers, only location dynamics. Now, at larger attraction values, you find the secondary maxima, which are characteristic of cluster fluid phase. These are typical snapshot of that cluster. I will talk later about how these classes are, whether they are rigid or whether they are dynamic. In fact, they are dynamic. Yeah, good. So we learned that the fixing this graph type distribution function characterize the visual graph size, and we will later show you that the graph phase and the size change dynamically for this system, and they are also influenced by certain mediated interaction, which is called hydrodynamic integration. All right. So to the next slide. Okay, how can we know something about the structure in this system? In this system, well, one way is with the neutron scattering, for example, you impinge monochrome neutrons on them, and under certain angle or certain scattering wave number, you detect the neutrons, and then you form what is called the differential cross section, which is proportional to a vector which is determined by the strength of the particles of the protein, and the so-called fraction vector. And this fraction vector is nothing else than basically the Fourier transform of the radial distribution function of that particles multiplied by the concentration of particles. This is the rate number, scheduled rate number, and it's the rate of all positions. Radial distribution function gives you the probability of finding the particle at the distance r from a given one. Okay. Now, we calculate this satisfaction factor using a so-called integral equation scheme based on this Leonard-Jones blah. I don't want to go into details. If you're interested, I can explain in detail what the scheme is in this calculation, meaning it's pretty accurate. And from that, you can obtain the very distribution function structure factor for our Leonard-Jones SALR potential system. Okay. Now, okay. Now these are the results of the abstract factor for three different attraction range values. These are all such that we are dispersed two effects, but there are no preferred classes yet visible. And as you can see, a very short low attraction or relative factors. Yeah, typical abstract factor with one maximum, which is roughly given Qn at a rate number, which refers to the mean distance between the bar. And then it was the base. I should say the lines are the result by this so-called integral equation scheme, and the open symbols are resulted by our MPC simulators that you can see there the line agreement. With increasing attraction, there's a secondary key form that's smaller range numbers, meaning larger distances, so-called intermediate order peak according to Montcasarena, but I refer to them as cluster peaks. But you should keep in mind that they are all clusters variable, right? It's just the tendency of all clusters which lead to a secondary peak here at smaller range numbers, which is referred to as a cluster peak. This cluster peak grows with increasing attraction. All right. But interestingly, there's an isometric bond that means independent of the section of all dispersed intersect at certain rate numbers.
Okay. Excuse me, I have a question. Is the way that you obtain the static structure factor, it was numerical or is it analytical?
No, this sorry. Simulations of course are numerical.
Oh, those
And
are
actually, I'm university has worked to be solved numerically. Especially also anatomy for the low relation or that type of potential. The potential is complicated enough that you can look at the distribution. It's numerical, but much faster than doing it by this NPC simulation. If you have the good base messages, use their line and we have a perfect description of that function. All right? Okay. Okay, this is for the satisfaction factor. Now it's for larger values of this attraction rate. So here, 5% and 8, we are already in the equilibrium cluster phase. As you can see here, the peak grows strongly with increasing attraction. Here I only show symbols because in this equilibrium cluster phase, where you have cluster, there are anti-integral equations that work. And there's a critical value in 2 dimensions, 3 dimensions, which has been detected by this tool of around Wagner, and Ron, they found that when this peak 8 is the value of 2.7, you find the transition between the distribution between the monomer phase and the equilibrium cluster phase. I will discuss that in more detail in context of 2 dimensions. All right. Yeah, these are of course structure factors which look a little bit complicated. You see here you have the preferred structural geometries like tetrahedral or plane trigonal glass, but it should not meant to mean that the glasses always look that way, right? This is just the well, this would minimize the energy, but not the energy. Actually, they are quite flexible. This is just a concentration of over 1 in these units, and we have here already a system which is in this space filling clusters. And all these are equilibrium cluster phases where you have this peak which grow in size, and you get additional peaks when you increase the attraction. This is the equilibrium cluster phase, right? Okay. Yeah.
I have another question.
Yeah.
You showed short distances on the radial distribution function, but have you measured what happens at longer distances?
Yeah, good point. Yeah. When you go here to local distances R.
Yes, like
Well,
6, 7,
that's certain distances R. If this happens is related to this here. Sorry. Which which are related to the distance between neighboring clusters. So this we can relate to the distance between neighboring clusters. So with decreasing R, you are looking into clusters, right? Into a single cluster, but if you go to others, then you are growing cluster correlations. Of course, they grow with increasing attachment, as you can see here in this slide. Okay, so then you've done something also about the cluster correlation. Okay. It's a bit tricky here to really disentangle that because we don't want to really distinguish. We start saying, I'm sitting on one particle and ask for the probability of finding another one. I'm not distinguishing whether this particle is sitting on the same cluster or sitting on a different cluster. So this information is a little bit worked out. It's not a cluster, individual cluster that is doing function. I'm showing you. Thank you for the question. Yeah. If you want to learn something about dynamics, you have to do a different experiment. But we can do, for instance, one measures this time-dependent extension of the dynamic structure of the time structure vector, which is called dynamic structure vector. And if you measure that at a certain time, you know which is short against the diffusion time of a particle across its own line here, R squared, not just a single particle diffusion coefficient. So at time short against that, you find that this function behaves exponentially in time with a Q squared dependent and so-called wave number dependent diffusion function. You do a little bit on theory based on a generalized diffusion equation, which goes under the heading of Small-Coffee equation, then you find that this wave number dependent diffusion coefficient is equal to the single particle diffusion coefficient times the ratio of two functions, a kinetic function which is called hydrodynamic and the static structure vector, which is nothing else than the dynamic structure vector for zero delay time. Now, this function is interesting for us because we can show that this function would be equal to 1 independent of the wave number in case that hydrodynamic interactions doesn't play a role. Now, what are hydrodynamic interactions? Suppose we have, actually Jan was talking about it yesterday, but can we show? Suppose we have a particle moves to the solid, the solid sticks to the surface of the particle, and that motion of the particle triggers a flow of motivation, which propagates quasi-instantaneously on the level of the motion of the particles. And this flow of motivation affects the motion of neighboring particles, and that's called hydrodynamic interaction. So it's a kind of strange type of interaction which is mediated by the flow related by the particles. With that, they influence our, and this interaction is long range. It can like one of the difference between the particles in general. Yeah, so we do the same experiment, but now dynamically, meaning that we have neutrons increasing on the center and under a scattering rate, now vector Q, you measure the scattered neutrons, but then you correlate now the densities of the neutrons, not at the same time, but at the delay time t. This difference dynamic structure. Okay, and as I said, from that you can induce at a certain time we know this hydrodynamic function. And if you look at that, and you see, oh, it's equal to 1 all the time, all of the wave numbers, hydrodynamic interactions play no role. If it is changing as a function of mu, hydrodynamic interactions become important. So let's calculate that one, which we have done. So you know that we have calculated S of Q again using this Einstein scheme, which we, as we know now, is very accurate. And for the hydrodynamic function, we use another method, which I'm not going into detail, which includes the hydrodynamic interactions. That we based on a method devised many years ago by Gerhard and Masur. We have a use of corrected method which corrects the set part of that, which is rather poor in the original method, but with that set part corrected becomes quite good. So what we got is not an eigenvalue function itself here, I will show it later, but this is background dependent diffusion factor. Why? Because this can be directly measured as a function of wave number units of time here. For 3 different values of epsilon from 2 to 6 is all in this per two place. And as you can see here, with increasing attraction for given concentration, then there's also a peak related cluster which grows with increasing attraction, and the two lines are the theoretical predictions here, and the simulation lines based on NBC are the symbols. So they find within statistical errors of the simulation is quite nice. Right? It's called the wave number dependent diffusion coefficient, and small wave numbers. This is what is called collective diffusion coefficient, which you find in a macroscopic gradient diffusion experiment. If you measure it at this wave number here and the second peak is, then it's called case diffusion coefficient, related to the neighboring case of particles around the particle, which limit the diffusion. Okay, so nice agreement between the simulation and the theory with our adjustable parameters. Again, we got that now for our concentrations. We go into the cluster fluid plate here, and you test that by the original symbol. By the way, when you compare this inverted triangles with this dashed line, then you see the difference in calculating this inverse diffusion coefficient with symbols and without interactions. You can see you make a big mistake going from the symbols to the dashed line when you do not account for eigenvalue interactions. But they are important. Yeah, there's another thing which is important is the lifetime of the cluster. Can you hear me brief? This is really a snapshot of a cluster in this equilibrium cluster plate. In units of the diffusion time across the diameter of the part. As you can see, that the cluster is highly flexible. It changes constantly in shape. It can also happen that it loses a particle or gets one or that two such clusters merge. All is possible. So this is a finite lifetime, and they change continuously. Right. So it's actually in order work on this system, but people thought they are limited, but no, they are very flexible. Now we have calculated the mean lifetime of a cluster in some units, diffusion time again, as a function of the attraction of epsilon, right? And this is squared are the symbols. These are the result of the EMC symbols with full amount of eigenvalue interactions. And as you part, this is the derivative logarithmic plots. And we will know with increasing attraction. So when you increase the attraction, right, then the lifetime of the cluster increases logarithmically with a strong dependence. And when you hit the value of epsilon case for this density state, where the system makes a transition from the fluid to the cluster fluid phase, then it's the key, and then it grows more quickly. So actually, it's not only the structure faculty which is the indication of the state transition. You can also look at the numerical lifetime and it changes with the peak, and then you see at that point the system makes the phase transition. But dynamically preparing to localize a phase transition from the dispersed fluid to the cluster. And as you add that, 2 days ago I talked to Ramon. He did similar simulation experiment, so to speak, using a method where I don't know which is much faster, and he finds the same thing. From that comparison, we learned that this criterion here is not really dependent on the hydrodynamics, so it can be used to produce a different simulation method, like Ramon, they basically ground dynamics simulation method to localize this point where a phase transition is happening. But you can also do it with analytic calculations. I mean, you know, potential has a minimum, and then there's a maximum, and then it indicates exponential. So you could consider a particle which is momentarily trapped in the minimum, and you ask yourself, what is the probability that it will go over this barrier? Over this barrier is staying out of that. this is standard grammar theory, taking back to Dutch. This grammar, if you do the calculation with hydrogen interaction with very simple, but integral, then you obtain this steps in line. Cool. Then you try to say maybe it's hydrogen is playing the role. So let's repeat that. Let's now put the particle in this potential minimum and ask yourself when you will stay on average out of the process potential maximum. But now we account for that there are some lucky particles which are hydrogen interacting with the central particle. But we account only for them on half airwise level. And this is so-called binary dissociation theory. And that is what this line which you obtain here, right? This line here. So this is Kramer's theory, and this here is this binary dissociation theory. And as you can see, it's also poor, especially at lower attraction, but when you go to higher attractions, it becomes better, which makes sense. Because if you have stronger attraction, right, this glass becomes stiffer. And also, what's really important in the methods is only the hydrogen interaction between neighboring particles. Not anymore the hydrogen interaction with overlapped or next particles. So it's actually understandable why this binary dissociation theory becomes better at higher attraction range. But overall, it's just good. Yeah. So we can summarize that the strong influence of hydrogen interactions on the cluster lifetime and the dynamics. You won't notice that if you would calculate that without hydrogen mass. You would by also making to underestimate the cluster lifetime. The dynamic clusters like one lifetime, of course, we are calculating that, and there's a peak here at the transition from the dispersed fluid to the equilibrium cluster phase. All right. With that, first, sorry.
Right, according to the computer. Right.
This computer. Okay, yeah, you're right. Okay, yeah, we have also just time. Okay, we have also comparing experiments on lysozyme solutions. So here we have experimental neutron scattering data, smart neutron scattering data of the starting structure factor for different samples. Here we have systems which are dispersed fluid phase, and the last one is for a system which is in this percolating phase where we form twice bimonomers. And this is also for different samples.
At what volume fraction are these?
The volume fraction shown here, sorry. They're rather low, something around 2.1. Sorry, I missed to put them in here. Around 2.1. Good. Okay. We have also done accompanying computer simulations. This is again the cluster size distribution function. And what we did is we fitted the starting structure factors by using our analytical theory, our integral equation theory. From that, we determined the interaction parameters, and from that, we calculated then the simulation. In this case, in the Monte Carlo simulation, the cluster size distribution function. And from that, we could identify whether we have a system in this dispersed fluid phase or whether it is in this random calculated phase. You see here for the sample function. Yeah, this is in this random calculated phase. You can also look in the years later, this distribution function. It also gives you additional information about the different phases. Yeah, this is the hydrodynamic function. This has been determined experimentally using so-called neutron spin echo experiments, which can be done only when you have a reactor available and a neutron spin echo machine available, like at the NIST Maryland. Okay, but what we see here is a comparison, direct comparison between our theoretical calculations and experimental data for different samples. These samples here are in the random calculated phase, all the others are in this dispersed fluid phase. And this is for different concentrations. I'm sorry, I forgot again to tell you that the concentration increases from top to bottom, so nearly increased concentration. Right? And as you can see at the lowest concentration here, there's very nice agreement between theory and experiment. And in particular, we predict here a cluster peak also in the hydrodynamic function. And this cluster peak here is also present in the small and neutral scattering data. So it's the first, this was the first experimental verification of our prediction. When we go to higher concentrations, the agreement becomes poor, although the ordering, I mean, what is about what, it still remains valid. We blame for this difference the fact that in our simple model, these are just no simulations, just this integral equation theory calculations, that we neglect the patchiness and the asphericity of the proteins. So this should be included, especially at higher concentrations.
What is asphericity? Sorry.
What
is asphericity?
Well, the particle is not spherical, really. Yeah, go back. Yeah. They're not exactly spherical, right? This is such a lysozyme protein. It's not really spherical. It's more shaped like a potato.
Yes.
And it has attractive and repulsive edges. And we only account for the we say on average this leads to a short range attraction, and the charges on them lead to a long range repulsion. And actually, when they come close to each other, and two hydrophobic patches face each other, this is like the attraction, right? So they have a preferential orientation towards each other, and this is not included now. Okay. And when you go to higher concentration, this non-asphericity and this patchiness matter, and we have not included that in this simple semi-analytical calculus. Okay. Yeah. Good. That's it for the two-dimensional systems, and in the remaining 10 minutes or so, I will now go to more recent results, actually very recent results, which we have done on quasi-two-dimensional systems. As I said here, we consider now these proteins to be confined to a plane. They can only move inside of the plane. They can freely rotate, but their motion is confined to the in-plane motion, and they're solvent on top and bottom of them, so they interact directly only with in-plane forces, and for that we use again this Lennard-James-Jones-Yukawa potential forces. But hydrodynamically, of course, they can also interact indirectly through the solvent which sticks out of that plane. That's why we call that a quasi-two-dimensional system. Right? Good. How can that be realized? For instance, with some extras, of course. Particles could be trapped at a liquid-liquid interface. Proteins are attached to a membrane. An example, actually, we use that model in a generalized way to discuss postsynaptic signal transduction in neurons. Or you have optical tweezer field, which confines the particle to be with the motion inside of this plane. The methods we are dealing with are mainly large dynamic simulations without hydrodynamic interactions. We also perform some multi-particle collision dynamics simulations, and together with Ramon and his team, we also looked into some specific thermodynamic properties where we use thermodynamic perturbation theory and Monte Carlo simulations. All right, good. Oh my God, this is really. But the phase diagram is totally destroyed here. I don't know why. There should be patches here visible. This was fluid phase patch, a random percolated patch. There should be an equilibrium cluster patch, and there should be a CP calculation cluster patch. And then there is here this line separating them. What I want to say is that the phase diagram roughly looks exactly the same as in 3 dimensions for this range of temperatures and now area functions. I'm sorry about it. This is visible.
Do you also have a binodal line there?
Maybe we have to see if it is getting better later. I don't know what happens in my computer. It works. So, okay, this is just a snapshot from the equilibrium cluster phase. As you can see here, there is this cluster form, and they are flexible and they readjust. Yeah, but we identified these phases as in the 3-dimensional state by looking at the cluster size distribution function. I don't have to, for instance, when we find such a peak here, we say, okay, now we are in the equilibrium cluster phase. So the first thing to mention is that for this range of temperatures and area concentrations, I mean area of a particle relative, or cross section of a particle relative to the area of the plane. But in this regime here, we find the same type of phases, right, as in the three-dimensional case, which does not exclude that there are other phases, like for instance exotic exotic phases, which can occur in two-dimensional systems, but not in three-dimensional systems. Okay. But here we have it again. Sorry. Here we have it again. Phases here, and these are again snapshots. You see here they have this random populated phase with this space spanning clusters. They don't consist of individual clusters. It's different here in the cluster population phase, where you find space spanning clusters which consist of smaller clusters. And as you can see here, a big difference to the three-dimensional case is that we have here a strong local hexagonal order, which is triggered by the quasi-two dimensions. All right, and here we have the equilibrium cluster phase. So fortunately, this picture works. We could do the same kind of, or we tried the same kind of things. You know, we have this different Leonard-Jones-Yukawa potentials, and we chopped them off here. So we chopped off the long-range impulsive part, replaced them by an effective square world potential. And for this effective square world potential, we calculated using thermodynamic perturbation theory, the binaural, and that looks quite nice. However, we realized that using thermodynamic perturbation theory in absolute terms, and we don't normalize by the critical point values, is flawed. Why? At 2 dimensions, the thermal fluctuations, energy fluctuations are much higher than in 3 dimensions. That's why criticality, for instance, is much more complicated in 2 dimensions than in 3 dimensions, and that's why you don't find the phase transition in 1 dimension, because the fluctuations are just too large. So actually what we realized is that we should do better here, and that's why we triggered a collaboration with Ramon and his team, where they use now Monte Carlo simulation methods to map out the phase diagram for Leonard-Jones for square wave systems and so-called mean potential systems with very short range interactions. It's a demanding task, which I'm not going to talk about here, because I'm running out of time. I did it a couple of 2 days ago in a seminar given in the group of Ramon, so I hope Ramon doesn't mind if I'm not going to details here. I just want to mention it's a very nice Mexican-German collaboration, which was triggered by both of us attending a conference in Wien, where we started discussing that. Okay, so let me leave this issue here. Okay, we can also look at forcing into criteria for transition from the dispersed fluid to the cluster fluid phase. As I told you, in 3 dimensions, as Gottfried, Casanedo, and Wagner found out the value is 2.7. We find also such a value which is smaller than 1.4. There's another criterion which is related to the width of this cluster fluid here. When this width here, or down width, is about width of the diameter 2, you also have to make a transition from the cluster fluid phase to the dispersed fluid phase. And this value actually stays hold in 2 dimensions. There's also the coordination number criterion. In 3 dimensions, it's 2.4 next neighbors on average, whereas in not unexpectedly in 2 dimensions, it's only 1.6 neighbors on average when you find such features. Okay. Now, how did we get this? How did we treat that peak here? Actually, it's something interesting I want to discuss shortly. So we describe this cluster peak here in a way which is also used to look into critical opalescence, but now not at the wave number Q0, but at this wave number QC, where this peak appears. So we say it's nice vector factor in the vicinity of this peak is given by this semi-Ornstein form with a parameter here squared, which should be related to the correlation length associated with that peak. Now, if you fully transform that back, that's a nice exercise in complex variable theory, which I did, you obtain this here. So this is the total correlation function, or in other words, up to factor -1, the Baire distribution function at long distances between two particles, as triggered by this interior, as you can see, it decays exponentially with a decay length, which is this down width length here, and then you have a oscillating factor with a wavelength is 2, or the position of that peak, which reflects the fact that you have here a microphase separation into regions, two clustered regions. But on top of that is an extra term which was missing in the regional discussion here, which is actually the term which determines the long distance behavior. It goes like 1 over r to the 4 in 3 dimensions. If you repeated the calculations in 2 dimensions, it's the same looking shapes, except that you have here a square root of r dependence here, and you have a 1 over r to the cube long distance behavior. And if you recall the theory of critical opalescence, here a critical point, and you find that this is exactly what is predicted, also at such a critical point, except for these factors here, and except for this additional. Now we have looked into many different fields. For instance, we looked into the next neighbor, the coordination number, how many next neighbors on average does do the different phases have. Of course, if you're on the cluster probability phase, you have the largest number of next neighbors, namely 4. And it's actually not surprising. This is a snapshot of such a space-filling cluster. And you see here you have double-stranded clusters which build up the whole space-filling cluster, and you have actually, if you count it here, 1, 2, 3, 4 neighbors on average. And that's why we have it. Yeah, and so on. And we can look at the orientational order here. I will skip that. It will also be discussed. And you can coordinate orientational orders at different times. And you find that they decay rather quickly in all the phases, except for the cluster propagate phase. And actually, for the cluster propagate phase, you can find that this ordering correlations decay even more slowly than what is observed what is observed in these hexatic phases, these exotic phases which only occur in 2 dimensions, where you have no long range translational order anymore, but still long range orientation order. Okay, good. You can also look into the square displacements. I will skip that. We can look into non-Gaussian behavior of this system, so which is the measure of caging. What we find is that this non-Gaussian vector here, which is the function of time, is largest when you have a cluster propagate system, and it's lowest when you are under dispersed fluid phase. It's similar to what you observe in our particle systems with pure repulsion, when you go from a fluid phase to a glassy state, and also this non-Gaussian parameters become very strong. This is actually the 2-dimensional analog of the 3-dimensional non-Gaussian vector. Yeah, okay, we can also look into collective dynamics. This is now a hydrodynamic function. So this is the structure vector again into 2 quasi-2-dimensional systems. And here we look now at the hydrodynamic function. You see it's totally different than the 3 dimensions, because as small wave numbers, h of q becomes very large. Something Jose Luis knows about very well. You have correct particles trapped between 2 clusters. You also look at the hydrodynamic function at small views. What you should observe is that this goes up. However, it depends on the distance of the glass plates. Okay, now you can make some simple analytic theory on that. For unbounded fluid, you find indeed that they have a divergence like 1 over q. Hydrodynamic function at small q in 2 dimensions. And this brings me to my large responsibility to explain that. Why is that in 2 dimensions that this hydrodynamic function diverges? Now, the point is the following. This hydrodynamic function at small q, this hydrodynamic function at small q, the very small q, has a different physical meaning. It's a mean segmentation property. Suppose we have a plane with particles in gravity, and you turn it by 90 degrees. And then the particles can move around the plane in the direction of gravity downwards. What happens then? And if the gravitational field is weak, or meaning that the particles have a mass which is more close to that of the fluid, and this sedimentation is slow. And in the case that the sedimentation is slow, this hydrodynamic function has more Q is nothing else than this sedimentation coefficient. And so if you now look at that, and here you see the following. The particles move on average along the direction of gravity now from right to left. And when this particle moves, it's pushing the fluid out of its way. Where can the fluid go? It can go along the plane, but it can also go out of the plane. And this is what the fluid does because volume is conserved. So there's a backflow pattern created by this particles moving on average in a direction, which goes back again to the plane and gives them a kick from behind, right, so to speak. So they get there's an effect that enhances sedimentation. Actually, to such a limit that in principle the sedimentation velocity should diverge. Of course, it cannot diverge for several reasons. First of all, the calculations based on so-called Stokes equation, which is the equation that hydrodynamics describes as static. And secondly, more importantly, is that you always have confinement here and here, some walls like in the glass plates experiments with Lewis, and they actually lead to the fact that this divergence is actually not a true divergence anymore. Okay, or you particles move a little bit out of plane, and also this limits this enhancement of H of U as well. Well, we could also look into the time development of the hydrodynamic function at shorter times where inertia matters, and nicely see how it develops. But this is another story, and I will stop now and come to my conclusions. We started and quasi-two dispersions of SALR particles. We used simulation methods without or with hydrodynamic interactions to see the different the influence of hydrodynamics. As you have seen, important that small wave numbers. We studied the safety diagram, clustering analysis. This is ongoing work together with our model, where we would like to see how the north-eventful extended north corresponding states operates in 2 dimensions. We looked to the dynamics where the hydrodynamics is fully developed, where we found this enhancement of the hydrodynamic function. We also looked at very short times where the hydrodynamic interactions is about to develop by the diffusion of vorticity in the fluid and by sound waves. This can be resolved in these simulations, and then we can nicely study the build-up of hydrodynamic functions. With that, I would like to stop, mention my collaborators. This NPC simulations have been done by Gerhard. Really thankful to him. I have interactions with this gentleman, this lady. The Monte Carlo simulations are done in collaboration with Ramon and Alexis from Guanajuato and Mexico, and they have experiments done. The group of Norman Wagner and Jon Yu and Doug Godfrey did many of these experiments. And you might ask me, have there been experiments on quasi-two-dimensional systems which could confirm our predictions? So far, none, except for its hydrodynamic enhancement, of course. But a colleague of us, Peter Lang, is planning to do experiments on membranes, where he is going to insert proteins, and the proteins can only diffuse along the membrane. And then we hope, with some modification of our calculations, that this would be experimentally confirmed, but we have predicted. With that, close, and thank you very much. And sorry about being so long.
Okay, there is time for some questions. So go ahead.
Okay, here I go again.
I know.
I don't know which slide it was, but you were showing some salary system comparing it. I know that your whole talk was
Closer to your mouth.
Oh, okay.
Thank you.
Can you go back on the slides?
Which slide?
I don't remember, but if I see it, I will.
Okay.
Just say stop.
Okay. No. Keep going. Thanks.
The quasi-2D or 3D?
No, it was 3D.
This is now the first part. Part 2, 3-dimensional.
Yes, over the next. No, go forward.
Over here.
Forward there. Do you recall what parameters you use for this double Yukawa potential?
Well, not exactly. No, I must admit I skipped them here because I didn't want to go in details. So I cannot. Sorry, I cannot really tell you exactly the parameters.
But
They were actually determined in the following way. I can just tell you how we determined them, and that's why I don't give them here. You know, not DAC provided us with starting structure factor. DAC group around normal. They provided us with neutron small neutron scaling data for the starting structure factor. Okay.
I'm sorry, I didn't understand.
Besides foreign data, they give us data for S of Q, right? And then we assume a certain interaction model. Now these guys use their favorite interaction model are short range attractive Yukawa, long range repulsive Yukawa. So we use that type of potential, not the one we used before, but which actually doesn't matter really. And then they know the salinity of the system, so that we can give an estimate of the range of the long range exostatic repulsion. And for the short range attraction, we had fit parameters. We had a fit parameter for the range of the short range attraction and a fit parameter for the interaction study. Right. The work fraction is known, measured. So we made a fit. So we calculated the starting structure factor for different parameters based on the Sierra-Hansen scheme, and then we fit them, right? As you can see, it's and from that we got a table of interaction parameters for that potential, and that we keep fixed in all our calculations. Yeah, for the size distribution functions, for the G of R's, for the displacements, and for the hydrodynamic function. We're all fixed. We didn't tamper around anymore with it.
My question was because we've been exploring this type of potential also, but it affects a lot the choosing part. I don't know how to say this. Like the order of magnitude of the parameters change dramatically the phase diagram of those.
No, actually it doesn't. I mean, the fact is that we have here competing interactions of very short range, attractive, very long range repulsive interactions. The repulsive part is still exponential, right? In both, you are asking about difference between the Jones Yukawa potential and this 2 Yukawa potential.
No, I am talking about the different, well, how, if the range of the attraction is greater than the repulsion, and how?
No, this is the point. Good question. The range of attraction is a small fraction of the diameter of the particles. At most 10%, less than 10%. And always less than 10%.
And the repulsion?
And the repulsion is 10 times. This can change. In our case, it's about 10 times the range of attraction or more. Yeah.
Okay.
Yeah. Okay. I mean, if you have a very short range attraction, like a system with very short range attraction and no repulsion, there exists an extended law of corresponding states, which tells you that if you know the volume fraction of the particles and the concentration, and if you know an attraction parameter and a so-called secondary coefficient, this fully determines the equation of state. This is called extended law of corresponding states. And this only holds for this type of potentials where you have an attraction range which is small compared to the size of the particles. Of course, on top of that, we have now this long range repulsion. But I don't think it is really matters so much how precisely you model short range attraction, because it's always short range in the sense only 1/10 of the. Yeah. So the general phase diagram doesn't change. The morphology of this phase diagram does not change in going from, I don't know, from a 1/r to the 550 power law attraction to a short range Yukawa attraction. That's the point. I mean, it's pretty universal in that sense that the morphology doesn't change.
Yes.
If you look at the precise values of the location of the separation line, of course, in absolute units, that could change. That could depend on how you on your specific model for the attraction part, for the short range attraction part.
Mhm.
Then, of course, it will be.
Okay, this is it seems that we are starting already with the workshop for tomorrow. So this was a great introduction. Would anybody else have additional questions? Yeah.
Well, if you increase the range of the revolt of interaction, then at some point you will lose the flux effect. Yeah. Well, how large it could. I mean, what is the minimum range of your revolt attraction to have flux? I think it's not only the minimum rate of the light of the benefit that they have to be completing. It means if we make more and more the short range attraction long range, I think the phase diagram changes and it becomes more different. I think you will get also I mean, in this case, when we have one short range attraction, the little get by node is mega state. The little get by node is mega state. And if you increase the range of attraction, and increase the concourse of certain upwards in phase diagram, and then eventually you will also have a stable with gas resistance. So we have I think that the morphology of the phase diagram will change. I cannot understand exactly how about stability of the crust. I mean, for which parameter we got. Maybe when the clusters become, if the range of the result becomes smaller and smaller, you are now going to talk about the life for life. Yeah. So make the result of the range of the result of the potential longer at some point you will lose your life. Yeah. But the question is, what is the parameter? I encountered. We didn't make a quantitative study on it. We were restricting ourselves to the limiting case. In the question, I cannot answer. But do these parameters fit with something what you would expect in biology? Well, no. I mean, this since we have a very long range requirement, like if we had to use a requirement to electrostatic repulsion, we have to go to something low salinities that we are well below leverage to find under physiological limitations. If you think about realizing what two-dimensional systems experimentally, my suggestion would be go away from biology, use the hanging drop, set up in the model like the microscope, for instance. You have particles, supercarbonated particles, you apply magnetic field, you get a long range dipolar repulsion, and then you add also polymers to that, as small particles, which also could be heavier than a solvent, which go to the interface with the interface, and they exert some division there. And then you have to go step in such a way that they are, but we can do that by changing magnetic field. So raft for formation of membranes in cells that is not connected. I don't think so. It is only to do the battery power.
Okay. How about anybody else has additional question? I didn't have one, but I would not do that. In one of your previous transparencies report, I don't know the important. You have the baseline, the lifetime of the clusters, and you talk about as a function of, I think it was the yeah. And you say for the algorithms, there is a phase transition. You said.
Well, we know that from discussion before, right? Based on the cluster type of supervision function and the width of the cluster B, that at epsilon equals if equal to 6, the system makes that just a transition. And then it is just an observation that if you look now at that lifetime, at that point when it makes the phase transition, that this logarithmic plot with the slope changes. That's kind of
But my question is that a thermodynamic phase transition or just a transition from one behavior to a different?
I mean, of course, on the basis of our relations and on the basis of this classified inclusion function, we cannot really say this is the fundamental phase transition. But people have studied that using density function methods.
Yeah.
And according to them, and some of them using three methods, so also questionable, whether they can really identify the type of phase transition. But what they say is that it's the genuine fundamental phase transition, first of all, first of all.
Yeah, because the quantity we're looking at there is the cluster lifetime.
Yeah.
And that is clearly going up very quickly after this point.
Yeah.
And my wonder is, wouldn't that be more related to a dynamic transition?
You can think, but according to what Ramon found, very recently simulation is exactly the same. I mean, not the same system, for different system. They also found that the cluster lifetime at a attraction value where one observes the phase transition, it also has a P. And then actually is reconfirming that it is not really, it's a dynamic criterion for equilibrium phase transition. It's similar to the Naegele criterion, right? The Naegele partial criterion. They find that at a breathing transition, which is a vertical transition, nothing to do with dynamics. At the long time to the short time substitution coefficient becomes 0.1.
Okay.
Right. So it's not no contradiction in fact. And the fact that it does not depend on hydrodynamics. So it's actually the I should say one should find it also with other questions. It's actually
Okay, if there are no more questions, let's finish the seminar. Thanking Gerhard for his talk, and this introduction is a great introduction for the workshop tomorrow. We look forward to it. Thank you very much for attending. Can I not go in? Oh, no.